When we were looking at subspaces, it seemed that a subspace and a span are the same, at least as R2 is concerned. Now you may wonder whether these two are always equivalent. That means that we have to look into two questions. First, is every span a subspace? And two, is every subspace a span? In this video we will answer question 1 and we will show that every span is indeed a subspace. But how about the converse? Well, let us look at question 1 first. We know what a subspace is. Subspace is a subset of Rn which has to satisfy those three properties. So now we wonder, if I have a span, does any span satisfies those three properties? Well, let us look at a span of two vectors, u1 and u2. Because the proof for a span of two vectors is exactly the same as the proof for a span of more vectors, just a lot more writing is involved, so that's why we will do it for a span of just two vectors. If a vector x is in the span, so if x is in H, that means that x is a linear combination of u1 and u2, so that means that you know that there are weights c1 and c2 such that x equals c1 times u1 plus c2 times u2. That's what you know for any vector in H. Now we wonder whether this H over here satisfies those three properties. Well, let's check. First property is a zero vector in H. So can I find c1 and c2 such that x becomes 0? Well, we can pick c1 equals 0, c2 equals 0. We can pick any weight we like. And then we get x equals 0 times u1 plus 0 times u2 equals 0. So, yeah, the zero vector is in H. First property is satisfied. Second, if I have two vectors in H, say x1 and x2, then I know both x1 and x2 are a linear combination of u1 and u2, probably different linear combinations. So x1 equals c1 u1 plus c2 u2, and x2 equals d1 u1 plus d2 u2. Then I wonder, what about the sum of the two? What about x1 plus x2? Is that also in H? Well, let's see. We can add x1 and x2. x1 plus x2 equals c1 u1 plus c2 u2 for x1 plus d1 u1 plus d2 u2 for x2. And now we can rewrite it. Take the u1 terms together and take the u2 terms together. Then I get a weight times u1 plus a weight times u2. But wait a minute, that means that the sum over here is again a linear combination of u1 and u2 with weights c1 plus d1 and c2 plus d2. So that means that the sum x1 plus x2 is again a linear combination of u1 and u2. So that means that x1 plus x2 is indeed in the span of u1 and u2, so in H. So property 2 is satisfied. Property number 3. If I have a vector in H, is any multiple of this vector also in H? Well, let's see. X has to be a linear combination of u1 and u2. And what do I get if I compute c times x? Well, we get c times the linear combination. Work out the brackets. C times c1 times u1 plus c times c2 times u2, second term. And then the trick is to put the brackets over here and over there, like this. Then we see we get a weight times u1 plus a different weight times u2. So we see that c times x is again a linear combination of u1 and u2. So c times x is also in the span of u1 and u2, which is indeed H. So c times x is also in H. And now we see that any span is indeed a subspace. How about the converse? Well, if every subspace would also be a span, why would we have introduced the notion of subspace then in the first place? Would have made sense to introduce this notion. So you can already guess that there are more subspaces than just spans, or that it might be difficult to express subspaces as a span. So, indeed, not every subspace is a span in the first place, and sometimes it's not so easy to write a subspace in terms of a span. So, any span is a subspace, that's what we have proven here, and not every subspace is necessarily a span.